Okay, good evening, everyone, and welcome once again. Today, we are going to look at convolutional neural networks. Yeah, so all of these weeks, we have been going through the basics of neural networks. We talked about the neuron, the perceptron, and then we talked about forward propagation, back propagation. And then we also even talked about the different kinds of layers, activation functions. We talked about different kinds of activation functions. We talked about different kinds of cost functions. We talked about different kinds of optimizer, right? And different kinds of optimizer methods, including the gradient descent and the various descendants of gradient descent, including the stochastic gradient descent, adaptive moment, SGD with moment, adaptive moment with weight decay, Nesterov moment, SGD with Nesterov, moment. So these are just ways as you are training your model, how do you descend that gradient slope in the most optimal manner so that you can arrive at the minimum value of the cost function as fast as possible and without ending in a local minimum. We talked about loss landscape. A loss landscape is, like a 3D plot of the gradient, the gradient of the cost function, so that you see that there are parts of, that loss landscape that you drop in and you can get stuck in a local minimum. So we've looked at a lot of this. All of this that we've looked at, starting when you talk about the neuron, the layers, the activation functions, those had to do with the basic architecture of neural network. Then when we talked about the, you know, forward propagation, backward propagation, optimizers, right? Cost functions. We're basically talking about the training loop. When you are training, what are the different challenges? Then we talked about the training loop itself. We talked about, the variance and bias trade-off and how to interpret it. That was still about the training loop when you're training the models. So all of that was to help us improve and get better, on how to train models. And I believe I shared a lot of different Jupyter notebooks for you to experiment and try out, right? So you can figure out how to train, what are the things that are important when you tweak these different aspects of the neural network. How does it affect training? How does it affect learning of the network? So we've done all of that, and it is something that you need to still continue to look at to improve, you know, the ability of yourself, to train networks and to get good at training networks. Okay. Now we're going to look at architecture. So when you hear things like a convolutional neural network, right? Well, that has to do with architecture. So we started off with a neural network that we call a fully connected neural network to solve that exclusive OR problem. And there's so many other kinds of problems that you can solve, right? With this fully connected neural network, right? That is made up of what we call dense layers, fully connected layers. So you just have multiple dense layers and you stack. But um, when it comes to solving vision problems, we have convolutional neural networks, and we're going to look at that. We're also going to look at a bunch of other different architectures of neural networks. So in this class, we are going to understand what is CNN. CNN in this case refers to the convolutional neural network. It is a special kind of architecture of neural networks that are optimized to solve what we call vision problems. In other words, for training neural networks to detect images, not just to look at the images, but to pull out meaningful um, features from the images and detect meaningfully things that are happening with images. And I'm going to do a bit of background in images as well, even though it's not in my slides, but I'm going to talk about images. What really are images? Okay, we see images from the standpoint of the human eye. We look at that, but we also need to understand representation, how images are represented in your computer. Because if you don't understand that background, then you'll not understand why convolutional neural networks are designed the way they are. And that is why I gave those videos to watch on, those videos would have given a lot of this background, but we'll still look at it. And then we're going to talk about the things that make up the convolutional neural network architecture, filters, feature maps. We're going to talk about the operators, convolutional operators, the pooling layers, and so on. And then we're going to look at modern CNNs, right? And compare with the older versions of CNN, the previous ones that were there. And then later on, we'll talk about transfer learning and fine tuning. Transfer learning is basically when you know, uh, you transfer knowledge from one net to the other. So that's what that is. Okay, so let's start off first with a defining and understanding what a convolutional neural network is. It's a special type of model, special architecture of neural network model. And in this case, we go into the boundaries of what we call deep learning models, right? And deep learning essentially is an area of neural network, sorry, an area of machine learning that deals with training of deep neural networks. So what is a deep neural network? By definition, a deep neural network is a network that has a lot of layers. There isn't any kind of agreed threshold that says at this number of layers, it is now deep, right? So there isn't like, oh, okay, if you have 5 layers, it becomes deep, right? Or when there are 10 layers, it becomes deep. But um, I think kind of is understood. In a way, you see it that um, at a certain point, you will have um, you just need a large number of layers to be able to achieve anything, right? So, for example, an exclusive OR problem, you can solve an exclusive OR problem with just 2 layers or 3 layers, however you want to look at it, right? In an input layer, hidden layer, and output layer, right? That's enough to solve an exclusive OR problem. So that can be considered a shallow network, okay? But to solve a vision problem, for example, then you would need more than 3 layers. In fact, you need more than 5. You probably need more than 10, okay? So by definition, once it gets to such large numbers from maybe 5, 8, 10, and above, then we begin to call those deep neural networks because they have deep in the sense that the number of layers are so much that you can consider them as deep if you're looking at them in a vertical orientation. Okay, that's where that word deep comes from. So um, you have uh, you have models that can have up to 1,000 layers, right? You have models that could have up to 22 layers. You have models that could have, um, you know, much less, much more, and so on. So in over time, researchers have found that when you add more and more layers, to neural networks and they become deeper, they are more computationally efficient, right? You get performance gains, okay? Um, but it comes with the risk of vanishing gradients, which we'll talk about later on. Okay, so anyway, so that's kind of going to deep neural networks. So that area of machine learning that focuses on training deep neural networks is what we call deep learning. And essentially, you can just think of deep learning as the subset of machine learning that focuses on training neural networks. which is what we are looking at. Not just the training, but the architecture and all of that. And the reason why it kind of branched out to be like a separate thing on its own is because there are a bunch of additional skills and, you know, nuances, subtleties that you need to learn and understand that applies to deep neural networks that will not apply to any other type of machine learning, training, for example, and we are talking about classical machine learning, right? But also even for shallow nets. So for example, things like vanishing gradients and so on, exploding gradients, those do not come up. Things like overfitting, right, do not come up with these other traditional methods. So the fact is that that's an area. So the CNN is a type of model. It's a specific architecture, and it's by design, it's designed to be able to extract features from grid-like data like images. Yes, there are other, if you have other types of grid-like data, you can still use CNNs on them. But in most cases, it always tends to be images, right? And there are architectural elements, right? There are elements in that. The main one being the convolutional layer. The convolutional layer uses a um a, a design principle or a mathematical principle or idea called a convolution, which we're going to talk about. And then you have what we call pooling, and then we also have fully connected layers. So we're going to talk about a bunch of this, right? The main idea is that the CNN is used to mimic how the human eye also interprets images or visual information that comes into it. So you use CNNs to do image classification, object detection, and image analysis. Okay, we'll see what the difference is in all of those. Okay. Um, yeah, so this is kind of a typical architecture of a CNN. Here is the input, which is the actual image. Then you have what we call kernels, right? Um, or kernels that are stacked up to form filters. Okay. Then you have okay, first of all, the input is an image map. That image map is separated into the different you could call them filters, right? Or the feature maps. Then you will now have a kernel that samples, or a filter that samples through those images and creates a new set of features. So remember, I've been saying that each layer in a neural network is essentially doing feature engineering based on input from the previous layer. It does some feature engineering and outputs a new set of features, right? That's really what's happening. And in a CNN, you see that very clearly because what is happening is that each layer, which is essentially a filter or a stack of filters, um, will generate a new set of features that form feature maps. And then the next layer will take that feature maps from that previous layer and use its own filters to generate a new set of features. And it keeps going like that, you know, over layer by layer, okay, until it gets to the end where you now have the last set of features are combined in a fully connected layer, which is what we looked at earlier on, to result in the classification. So we are going to look at all of this in detail shortly. So the question you would ask is, why don't we use fully connected networks for images? Why don't we use that? Why did we have to figure out a different architecture, right? The convolutional neural network or the convolutional architecture to do that. Now, the main reason is that images are large amounts of information. So, um, images are represented using a vector of numbers, okay? And I'm going to kind of um, go a bit into it, the details of, how images are represented, just to explain this to you. Let's assume that you have a normal picture, right? So if you look at images, you see that there's what we call image resolution, right? Images have resolutions. And the image, the resolution is basically a number that tells you the number of pixels that make up that image. So you see a resolution, a number like 224 by 224. What this means, it has 224 pixels along the X, the horizontal side by 224 pixels along the vertical side. So if I let me try to represent this, right, using my favorite painting tool, which I have used before, but I'm going to do a whiteboard. So let's look at it this way. If you take a simple image, a simple image, think of whatever you could have in this image, and we could just use an image of a cat. Okay, so let me just bring in an image of a cat. In a lot of these things, people always like using images of cats. I don't know why. There's this craziness about cats. Okay, so people like using images of cats. So I'm going to just follow suit. So if you notice, when I first pasted this image, it was really very small. Okay, and so I'm going to make it a bit bigger. You could actually look at the image. Let me see if I can find the image property. Um, yeah, I can't find the image property, but there are some apps that you would be able to check this image property, and you'll be able to see something like um 200 by something like one two normally, okay, let's say 1024 by 756 or something like that. A number that basically tells you the width of the image and the height. Okay. But when we say width of image and height, the question you should be asking is um width of image and height. What is the width? Width in what measure? What are we using to measure the width? Is it is it in inches or what? You understand? So you could say, okay, the width in inches. And actually, when you're talking about image, yes, you can also talk about things like the width in inches. Okay. But even when you are talking about width in inches, it always translates back to um pixels. Ultimately, it will become width in pixels. So what this effectively means is that this image is actually going to be divided, okay, into a grid. That's what you actually have. You have it as a grid, okay? And let's see, I'm going to try to represent this in a way that I hope this image is clear. So we go with a grid, right? We go with a grid. So I'm just going to make a very rough grid. In the real sense of things, right? This grid is much smaller. In other words, the lines are much closer together, right? But I don't have enough time to draw all of this. Okay. So you have a grid like this. Okay, you have a grid like this. Now, typically, the actual deal is that, and I'm going to zoom this particular cat image up to a point where you are going to see the individual pixels because a pixel has only one color. So if I were true in this my grid definition, right, you would see that it is really just there should only be one color. So let's say, for example, I have this grid. I'm taking one piece of this image, right? I'm taking one piece of this image. But the truth of, in reality, if I take one piece of this image and I post it, this is what you see, right? I'm going to zoom in. Now, I can actually continue zooming in until you see the individual pixels here. Even though this is being smoothed out, okay, it is being smoothed out. But I can keep zooming in. As a matter of fact, I can keep zooming in until you see this as individual pixels. We can keep zooming in until we get to a point where you are seeing individual pixels, right? A pixel is just a single square. You can see this kind of makes it look like it's a pixel, but a pixel is a single square that has a single color, right? And you now find that an entire image is made up of squares, those single squares like that, single pixels like that, that are kind of stacked together vertically and horizontally to form a grid. And there are different colors. Okay. So now how do we represent pixels? Because remember, everything in the computer is represented as ones and zeros. Okay. Um, they are represented by numbers. Okay. They are represented by numbers. So here's another image that kind of gives an idea of that. If you look at this image, this one is really exaggerated, but this is a very nice one. So this is a cat, and this cat is what we call it's pixelated. The reason it's made so that we can easily see the pixels. This is how it will look like if you were to zoom, if you were to use a magnifying glass and magnify the individual pixels on your screen, whether it's your desktop or laptop screen. Right now, the pixels are so tiny, it will be really difficult for you to see unless you really zoom in. For example, um, in a typical screen like mine, I'm going to show you the size, my screen resolution. So if you go check your laptop, you will see numbers like this. Let me put it up again on screen so that you can see. You see numbers like this. If you see a number like this, okay, 1920, this is what we call the resolution. So what this means is that you have 1920 pixels. This is the X resolution, and this is the Y. Okay. So X on the X axis of your screen. So just think of it like that. And the Y, that's the horizontal. And so the first number always represents the horizontal, while the second number represents the vertical. So what this means is that on the horizontal side of your screen, right, you actually have 1920 pixels, right? But on the vertical side of your screen, so on the horizontal side like this, you have 1920 pixels. And on the vertical side, you have 1080 pixels. So just think of how we managed to fit, 1900 and think of it, right? How did we manage to fit 1920 pixels, from this end to this end? Okay. So that is what that resolution means. The resolution always refers to pixels, and the pixel use the letters px, okay, to represent it. So if you were able to zoom in, right, to that level where you could see each pixel individually, right? This is what a pixel would look like. A pixel will look more or less like this, you know, a single one of these. Okay. So you could say a pixel could be this. And a pixel always has to be, it's a square. A pixel is always a square, right? It doesn't have any other shape. It's always a square. And it's the smallest square, the smallest subdivision. So you could think of it like I have zoomed in up to a point where I can see a single pixel, and this is the single pixel. Okay. So this is a pixel, and this pixel, the color is black. And then this is another pixel, and this pixel, the color is white. And then this is another pixel, right? And this one, the color is black. Here is another pixel, and the color is cyan or some, so pixels have colors. And the colors in pixels are very broad because the human eye is capable of perceiving, I don't even know, I can't remember, I think it's 12 point something million different colors to differentiate, right? So, what basically, in order for images to be photorealistic that a human eye can understand, you actually need to be able to represent those colors, right? So, um, yeah, so depending on the you have to be able to represent those colors. So, computing these days allows you to be able to represent close to that, about, yeah, 12 million different color, you know, variations. In other words, we should be able to represent colors. So for those of you who have had any previous experience, with programming, especially front-end programming, you see that we actually use certain numbers to represent colors. Okay, we use certain numbers to represent colors, and those numbers are called, hex colors or hex color numbers. So for example, you could we use the number, um we use a number like, you know for example, red. They have a system, right? In computing, we have a system in place. It's called RGB, right? RGB basically means red, green, and blue. And this is because, um, of course, scientifically, it has been proven that by combining these three colors, red, green, and blue, additively, you can generate any other color, right? And the color well, yeah, if you combine all three additively, you get, black. And then if you have none of them, you get white. And then combining different degrees of them will give you different colors. Okay. And that's how colors are represented. So colors are represented by numbers in computing. And the numbers range from 0 to 256. So the 0 means that particular color is totally absent. 256 means that particular color is fully present in its highest saturation. Okay. Then any number in between. So, for example, if I want to have a little bit of red, you know, green and blue, then maybe I can say 13 amounts, 13 over 256 of red, right? Then 20 over 256 of green, and so on. Okay. So those numbers are what are used to represent the color of a pixel, right? Okay. So I'm actually going to just show you an example of how this works. And we could do it with Python, right? And I might actually just do it with Python. But let me just give you an example of an RGB color mixer. So you can check this out. This is uh, um, a tool that allows you to play around with the RGB color, different colors, to understand how the numbers, how you mix them and they translate to colors. Okay, so So just take it. I'm going to try a few things just to explain, you know, um, colors. Okay. So if you look at this, right, this square here, just think of it like a single pixel. Okay. So if it's a single pixel, for us to determine the color of this pixel, we can mix different quantities of red. The first number is always the amount of red because it's RGB. The second number is the amount of green. And the third number is around amount of blue. So by just changing the different proportion of, red, green, blue that you mix, okay, then that will determine the color. So for example, if I remove green completely and I remove blue completely and I put the full red, you can now see that we get all red. That's 25500. So like I said, there's 256 degrees. It starts from zero. Zero means it is absent. That particular color is absent, totally absent from the mix. While 255 means it's fully the complete, like 100% of it is in there. So we start with this. 25500 means if it's all zeros, it's black. Black means they're all absent. If they're all present, right, it means it is white. Okay, if they're all present, then it's white. 255, 255, 255. Okay. Then you can now mix different colors. If you mix all of red and all of green, you get yellow. Okay, again, remember this is additive. For some of us, if you're a painter, you'll be wondering, why is it this way? In painting, right, the three primary colors are actually red, yellow, and blue. It's not RGB, it's RYB, but that's subtractive color mixing. And I don't know why they call it subtractive, because you're actually mixing the paint, right? So you're adding. But in physics, they call it subtractive. But additive is when you are shining light. This is when you are talking about lighting, when you are shining lights of different colors, right? So it's something to remember. Okay. So that's it. Additive color mixing combines light, which is RGB, but subtractive color mixing combines pigments, right? Which is ink or paint. Okay, so you can go check that. So for subtractive, the primary colors for subtractive are red, yellow, and blue. In case you did fine arts and you're not asking me, wait, what they taught me in fine arts was that the primary colors are red, yellow, and blue. That is true for subtractive color mixing. And that's pigments. But additive color mixing is when you are shining colored light. In that case, and it's light we are dealing with, because pixels on a computer screen, what's coming out of your screen is light, not pigments. So in additive color mixing, red, green, blue are the primary colors. And when you mix all of red and all of green, you actually get yellow, which is the converse of subtractive, where if you mix all of red and all of yellow, sorry, if you mix all of blue and all of yellow, then you get green. So yeah. So if we now mix all of green, right, and all of blue, then we get cyan. Then if we mix all of blue and all of red, we get magenta. Okay. And like I said, if we mix all three, we get white. If then you can now start having different gradations of color by just changing how much of each you mix, right? The more of blues you mix, the bluer the color will be. The more of red you mix, the more magenta it will be. The more of green you mix, the more cyan will be, and so on. So you will get, if you do a simple combination permutation of this, you'll find that you're going to get like over 12 million different colors, right? Based on this. Okay. Um, so you can also go and check that, right? So that's kind of that's a kind of, summary. 16, a total of 16 million colors. Yes, that's 256 raised to power 3. 256 times 256 times 256. That will give you about 16 million colors or so, just above 16 million colors. So this is how colors. So you start off by identifying how we represent colors in your PC. You represent colors by this combination. Now, typically in programming, these colors are written as hexadecimal. So you now have hexadecimal numbers, 0F. This 0F is the red component, and 0F corresponds to 15, which if you think about the hexadecimal for 15 is F. Okay. Then the next color is DD. So DD represents the green component, which in hexadecimal corresponds to 221. And then DE, DE is the blue component. Again, in that order, RGB, and DE also represents decimal number 222. So you can see DD and DE. So by representing this, by putting these three hexadecimal numbers, okay, with a hash, we have represented color. Or by using decimal, right? Same thing. It's just the same thing, it's just the way it's represented. The decimal, the hexadecimal is more compact. Now, there is also an extra addition that has been added um, in modern times. We call it RGBA. So RGBA, the A means alpha. And alpha in this case represents what we call transparency. So we have seen that in real life, there are, there are objects that are transparent. So even though they may have color, but light still passes through them. For example, glass, and so on. Of course, basically glass, but there are other kinds of objects like that. They have a color. You can have a blue glass, but light still passes through it. So in order to be able to represent such situations, right, where things are transparent, a transparency aspect was introduced, and that makes it now RGBA. Transparency is a number from 0 to 100 to represent how transparent that color is. 0 means it is totally transparent. That means you can see completely through the color, and you basically you will not see the color. 100 means fully opaque. Opaque means you cannot see anything else beneath it. So transparency is just a measure of how much of the color in a previous layer can you see, right? If you took this color and put it on top of another color, how much of the color under it can you see? That is what transparency is. So that's kind of a primer on how color is represented. So this color now is used to represent a single pixel. So an image is now a grid of these colors, right? That shows how these different pixels of different colors now combine to make an image, right? So that's what, that's basically it. Um, and when you look at that, it now makes it really easy for you to see that, yeah, I have, um, I have 1,000. So if you go back to what I just showed you here, this has 1,000, um, it has 1,920 pixels, okay, on the horizontal side, and then it has 1,080 on the vertical side, okay. So is the that is the dimension. That's the number of pixels. So if you do this math, you see that the number of pixels you have here is 1,920 times 1,080, which is close to 2 million, right? If not more than 2 million. It's probably over 2 million, right? That's the number of pixels. So this is a like standard image that we are dealing with. So let's go back to the question of how does this fit in with, how do we now train a neural network? So remember, when we were talking about feature engineering, we said that neural networks only deal with numbers. And of course, everything in a computer is a number. All the information that you see are stored, eventually are converted into a number. So everything has its format, but they are basically numbers. Now, a small image that has 224 pixels on the horizontal by 224 pixels on the vertical has a total image size of 224 by 224 by 3. Why do we have this times 3? Because of course we can understand 224 by 224, 224 times 224, right? If you have something that's 224 rows and 224 columns, then the total number of cells will be 224 times 224, right? But why do you have 3? Because for each pixel has 3 channels. The channel that represents the amount of red that is in it. Remember, red is 0 to 256 or 0 to 255. That's one channel. You have another channel that represents the number of greens, the amount of green in that pixel, okay? And then another channel represents the amount of blue. In fact, there should be 4, right? But we're using 3 here. If we count the alpha channel, which is the amount of transparency. So for you to represent all of that, okay, you will need a total number of inputs. The total number of inputs into the neural network has to be 224 by 224 by 3, because every single pixel has to be represented. And remember, a pixel is a stack of 3 numbers. So this is a number of numbers that you have to send into the input. Okay, and that gives you about 150,520 input values for a small image. So just go and check out the size of this image, how it will look like, for you. So that means if I wanted to use PyTorch just to do a simple image recognition, image training model, okay, it has to have a total number of 150,528 inputs, right? Not like exclusive for that has only 2 inputs, okay? Then for you to now train this model to do any classification, that's the number of inputs you have to put in here, right? And then if you wanted it to classify 4 outputs, okay, you have 4 outputs, but of course you need a hidden layer. So let's assume the hidden layer to extract more features is just 1,000 neurons, which by the way, I can tell is far from being enough, okay? So 1,000 neurons in your hidden layer. Each each neuron has 150,528 inputs. So you do that math and you find that we are going to have 150,528,000. That will be the total number of parameters, because each input in a fully connected network, each input needs to have this number of each neuron needs to have this number of inputs. Okay. So that will give you the total number of weights. Basically, you have to have a weight from each neuron to each input. You have to have a weight. So remember what I said. The total number of parameters for each neuron is going to be the number of inputs, right? Ni times the number of neurons, or the number of outputs, you might as well say, because the number of neurons is, of course, each neuron can only give out one output. It can't give more than one output, right? Because the output for a neuron is basically the state of that neuron, the state. So each neuron corresponds to an output. So number of inputs and number of outputs, that's the total number of weights that you have. And if I have 150,528 inputs, and I have 1,000 neurons, which corresponds to 1,000 outputs, then the total number of parameters or weights that I will have will be this, right? We didn't count biases, by the way. There will be 1,000 biases because each output needs a separate bias. So it will be 150 million, approximately 150 million weights for just one layer, for just one layer. So now imagine if you had like a deep neural network that had 3, 4, 5 layers. That would mean 150 million times 5 layers, right? Well, that's not exactly very accurate. I can't just multiply it by I have to calculate the parameters for each layer, because the next layer might have a different set of different number of inputs and different number of outputs. So it's always going to be Ni times No, right? Okay, you do a summation of Ni times No over the total number of layers. So let's say L, where L is each layer. Okay, so you're going to end up with a summation that says Ni times No for L equals 0 to the number of layers. So you're going to sum all of that, and that will give you a total number of I should actually do plus 1, plus NO here, because NO, you need the NO is here is the number of biases. So it's actually Ni times NO plus 1, right? but that's just going to the maths of it. So with this large number of weights for just one layer, it will be very slow to train this kind of network, and it will need massive amounts of data because like each layer is learning something different. It doesn't even make sense. So for example, in image recognition, there is what we call spatial spatial um um we'll look at it later on, right? What it means before I go into the jargon, it basically means that um the the image of a cat is the same, okay, irrespective of where you place it. So let me um let me show you an example. Um so let me show you let me go to this. Like if you look at this image of this cat that I have here, let me just bring this back out. I somehow managed to merge these two layers. So um but look at this cat, okay? Let me just take it. Okay, let me take not this smaller pixelated cat, but the original big cat. Okay, I take the original big cat, and I'm going to go to another part of my board, and I'm going to paste it here, right? And then I'm going to move it around. Now, the point is that as a human being, you see this image, you recognize that this is a cat. It doesn't matter where you place it. If you place it here, you still recognize it's a cat. You only realize that it has been moved to this other location. If you place it here, you still recognize it's a cat. If you place it here, you still recognize it's a cat, right? So this is one of the key properties of vision, of human vision, right? The fact that the spatial location of the thing that you are looking at, right? The location does not really matter. Okay, you are still able to identify what it is. Okay, irrespective of where something is placed, you are still able to identify where it is, right? The technical term for it is translation invariance. Translation invariance. What this means is that translation in this case is not translation of one language to the other, but the mathematical definition of translation, which means moving from one place to another, right? The physical positioning or the positioning in a particular space, a coordinate space. That's what translation is. So if you move the cat from one place to the other, it is invariant. We are still able to identify that it is a cat, irrespective of where it is placed, right? Now, the problem with using a fully connected network in this case is that that translation invariance does not exist. If you place a cat here, right, and you place the same cat here, it will not see them as the same cat. It will give you two different classifications. So that's the other problem. So for you to be able to train a network to be able to detect a cat, you have to have data that you have a cat here, you have another cat here, you have another cat here, and all of that. And it's easy to overfit because of the large amount of parameters, right? So that is the main problem with using a fully connected network for detecting images. So, and the main reason for that, I talked about the special invariance, is that if you train a fully connected network, every pixel is treated as if it is independent, as if it is on its own, it is different, right? So the fully connected layer does not also understand that nearby pixels may be related. You understand? For example, if the pixel is part of your eyeball or your eye, right? A pixel that is black will be surrounded by pixels that are black or very close to black because color doesn't suddenly change, okay? It's a graduation. So in images, nearby pixels are always related. They always have typically about the same color or close to the same color, the same transparency or close to the same transparency, and so on. And then patterns also typically repeat across the entire image, right? Patterns that make up like borders or like eyebrows, for example, or the boundary between one object and another, those boundaries also have patterns. So those patterns are similar. And like I said, a cat in the top left and a cat in the bottom right are the same, but in a fully connected network or yeah, fully connected, they will be completely different. Okay. Then the other thing is that for you to be able to train, you would have to flatten the image because a a, a fully connected network can only work with flattened data structures, no matter how you do it. Remember, when you look at this is a flat data structure. It's not a two-dimensional data structure, it's flat. So you will have to flatten. Once you flatten a data structure, you lose that two-dimensional relationship. Like we said, things are around the same spot in a 2D image. Okay, they are similar. We'll lose that two-dimensional information. So you end up with a flattened long vector, dense connection to the next layer, and then you're going to have millions of weights, like I have shown here. Well, this is just a sample, but it will be a lot. And then, like I said, two identical patterns are in different locations are treated differently. Okay. So researchers came up with something better and said, no, this won't work. Let's come up with something better. So they came up with a concept of the convolution, which allows you to look at small regions, pull information from small regions, and put it somewhere else. And then you reuse the same pattern detector. So you're not going to train a pattern recognizer. So essentially, you have what we call kernels, right? A kernel is essentially a pattern detector that detects patterns in an image. And it detects a pattern of one kind because you are using the same kernel across the entire image. We're going to look at that. So we are going to talk about that. And then the across each layer, first of all, across each you know, across a particular layer, right? You have a 2D structure. That 2D structure, you can then run across the 2D structure and you can get patterns from it. And then from the 2D structure, the patterns you get from it forms another 2D structure, right? Which you can then still run the kernels across it and get another 2D structure. So essentially, each 2D structure that comes out from a particular kernel forms the output of that layer, of that convolutional layer, and is sent to the next layer, the next convolutional layer, which also take the 2D structure that comes from the previous layer and scans it as well with a kernel. So we're going to talk about that shortly. So at the end of the day, the benefits, why we don't use fully connected is this is more or less a recap of what I just said, right? The There's local connectivity. So there's convolutional neural network will only focus on a local part of the image at a time. That way, you are able to have networks that the amount of parameters are much less, much less, vastly much less. Because think about it this way, and we're going to look at that shortly when we talk about convolutions. Think about a situation where you have this image, like we said, like I showed, that is 1024, or sorry, 1092 by 1000 and, you know, 24 or so, right? If you were to calculate the number of parameters, it would be huge, right? But I now take a smaller, um, you know, the network I'm using to scan that image is smaller. It's maybe like 3 by 3 or 5 by 5. Then you can see that the amount of weights that you have to learn is much less. Okay. And we're going to talk about that. So, but you now have a lot of those 3 by 3 and 5 by 5, swatches that you use to scan across. And that allows you to, and each of them would be dedicated to just identifying a particular type of feature. So by the time they identify a particular type of picture, they now send that to the next layer. So like I say, it's feature engineering. So the CNNs will only connect to a small local region, what we call a receptive field, rather than trying to look at all the pixels at once. It only looks at a small, subset of the pixels, very small subset. But it looks at it at once, then it moves to the next subset of pixels like that in an orderly manner. Okay. So what that does is that it allows that particular neuron, right, to just um, focus and understand local spatial patterns, right? Like edges and textures. We are going to look at that shortly. Then parameter sharing. So parameter sharing, like I said, is you use the same neuron or kernel as we will look at. It learns it learns the same thing across the entire image. So this significantly reduces, you are training those, and when you train those kernels, it only um you don't need to train different weights for different parts of the image. You use the same set of weights to go through the entire image. So the entire image is sharing the same set of weights, to identify the same kind of pattern or components or aspects of that image by looking at the pixels. So this significantly reduces the total number of parameters, making training more efficient and reducing overfitting compared to dense, fully connected layers. Then the translation invariance, which I talked about, is because we have shared weights, right? And pooling, we are going to talk about pooling. The convolutional neural network can recognize features regardless of their exact position in the image. So whether it's at the top left, bottom right, middle, or somewhere at the edge, it will still recognize, because when you take this kernel, right, that has a shared weight to view anything that it can detect, it will detect it irrespective of which part of the image it is. Okay. So think of a kernel as a neuron. It's not really a neuron per se, because a kernel is actually a stack, is a number of neurons. If it is a 3 by 3 kernel, that's 9 neurons that make up that 3 by 3 kernel. If it is a 5 by 5 kernel, that means it is 25 neurons that make up that 5 by 5 kernel, right? But you can see it as a meta neuron kind of, that, is arranged in such a way that it can see things that it is trained to see. Because essentially you are training that neuron, that meta neuron, if you might call it that. A kernel is basically a grid of neurons, and you have trained it to recognize some specific patterns. So wherever it sees that pattern, it is going to recognize it. Then we have the hierarchical feature learning, which I'll talk about later. Hierarchical feature is, like I said, every layer, right, does feature engineering for the next layer. But the interesting thing with these layers is that you are not hard coding the feature engineering. The neurons in that layer are learning the features on their own as you are training the convolutional neural network, the entire stack of neural networks. Each layer begins to learn to identify specific features. And when it identifies those specific features, it sends it to the next layer. So if it sees that feature in a previous layer, it is going to give ones, ones, ones to the next layer. If it doesn't see that specific feature, it's going to send zeros. So think of each kernel as a feature identifier that is trained. As you're training a neural network, you're training that kernel. It is learning to identify a specific feature, and it is now able to do a kind of classification and send that classification to the next layer and say, okay, on this layer, I have identified an eyeball or a nose or a mouth. But it actually starts with more primitive, like I've identified a slanting horizontal line or a straight horizontal line or a vertical line, and all of that. So each layer will identify features and send those features that and it has identified to the next layer. So deeper layers will now combine those features of uh, earlier layers, previous layers, and they will use it to identify more complex structures. So you now have a situation where every successive layer in your deep neural net, in your stack of layers, is able to identify more complex structures because the layers before it have identified the simpler structures and sent those. Then the layers that come after will learn more complex structures and send it, and the next layer will be able to learn even more complex structures, more complex features. And it just keeps going like that, sequentially over the layers until at the end, you now have the final layer being able to identify very complex features on an image. Like saying, okay, this is a dog or this is a cat. The idea of a dog or a cat is a combination of lots of different features of what makes up a dog, or what lots of different features of what makes up a cat. So what has happened is that the subsequent or consecutive layers, right, each are able to identify from simpler to less simple to less simple to complex to more complex to more complex and so on until it's able to combine all of those and come up with shapes, objects, and detecting even dogs and cats and so on. That's really what makes the convolutional neural network so powerful and being able to identify these features. Okay. Then the other advantage of CNN is it reduces overfitting because you are no more having fully connected, right? The number of parameters is much less compared to the amount of data. The amount of data corresponds to the number of pixels in the image times the number of images that you are sending it, right? Well, okay, the number of pixels make up the features, right? The amount of data is the amount of pictures that you send it to train on, right? So the weights that are interconnecting each layer in a convolutional neural network are not the full complement of weights because it's not a fully connected weight network or layers. So the tendency of overfitting is much reduced, right? So the other thing that you use for reducing parameters, apart from the fact that we're just using CNN, which the architecture itself means you're using less parameters, but the other thing is that you have pooling, spatial pooling, and then shared weights. Sharing the weights acts as a kind of regularization. So remember, when we're talking about regularization, we talked about um, dropout. So in dropout, you have a situation where some of the neurons are dropped out during training, during the back propagation, so that there are alternative pathways to the same knowledge. That's the same thing that's happening. It's basically what we call shared weights, right? Or shared knowledge. Well, it's kind of converse, but shared weights, you are using the same way to learn different things. Okay, so the tendency is that it is generalizing, it is learning what is common across all of those things instead of the noise. The noise gets eliminated. So that helps with overfitting. The same way that regularization, dropout that reduces noise helps with overfitting to reduce overfitting. Okay. So CNNs can generalize better to new unseen data compared to fully connected networks, which will have very high parameter counts and can overfit. So all of this is a summary of what I've just said. The ideas behind the CNNs, we have the local receptive fields. So the CNN neurons, which in this case are the kernels, they do not see the whole image. They see parts of the image. But those parts of the image are given to it in sections, right? So each neuron will look at a small window, like I said, 3 by 3, a subset of the pixels, right? Or 5 by 5 subset of the pixels, right? That small window is going to scan through the whole image, okay, from the beginning to the end, and then go to the next line and scan from beginning to end, go to the next line. Think of it like a typewriter, how it scans, right? And this matches how images work because in images, edges are local, text corners are local, textures are local. The edge of an image is local, it's only one part of that image. The edge is not okay, so not the edge of an image, sorry, but the edge of let me be clear, the edge of objects in that image. Okay. So what I mean by edge, okay, is if you take an image, right, the boundary between different objects or parts of objects in an image, okay, make up what we call edges. That's what we call edges. So for example, the boundary between the lips, the upper lip and the top of the mouth is a good example. That's an edge. The boundary between the eyelid and the eye, that's an edge. Okay. The boundary between your cheek and the hair, or between the ear and the hair, that is, or the boundary between you know a door and the wall, those are edges. So edges, from an artistic standpoint, an edge, if you are an artist and you wanted to sketch a picture of an image of someone, anything that you use your pencil to draw as a stroke, right? Or your pen or your paint brush to draw as a stroke, consider that an edge because you are using it to differentiate different parts of an image. So edges are local. That means they are local, right? Corners are local. They are not global. That is, they are local to specific sections of the image. Textures are local. Okay. So that's the first part. We talked about weight sharing. So weight sharing is happening because we're using the same filter in different parts of the image when you are scanning the image as part of the convolutional neural networks operation. Okay. Whether it's at the top of the image, in the middle, or the bottom, you're using the same filter to scan. Okay. So if a vertical edge exists anywhere, the same detector will find it. And detector in this case is a filter that has been trained, and is able to detect specific features. So you can have a filter that after it's been trained, what it specialized on or learned to do was to detect, like I said, diagonally slanting edges, left to up from upper top left to bottom right. Okay. Or a curved, you know, uh, edge, So we're going to look at some of that. So if a vertical edge exists anywhere, the same detector will find it. The benefits of weight sharing is that you have fewer parameters because you're using the same weights to detect features in the entire image. You're not kind of each part of the image have its own dedicated weight. Faster learning because with fewer parameters, your model will learn faster. You have less the computational need is much less, so you always learn faster. The speed of training of any model, right, any neural network model, depends on the number of parameters. The more the parameters, the slower it will take for you to train. The less the parameters, the faster it will take to train. Better generalization, like we said, because the shared weights act as a kind of regularization. It has a regularization effect by eliminating noise and allowing the model to just focus on the characteristics that are common, across the entire picture. Okay. Then we talked about spatial hierarchy of features, where we are saying that because the CNN learns in layers, each preceding layer, right, learns some features and sends that feature to the next layer, whether it has detected it or not. Then the next layer will build on what the previous layer had learned. It will learn more complex features by combining the simpler features that previous layers learned and is able to learn more complex features. And it will also identify those complex features in the same image and pass it on to the next layer. So for example, the first layer will learn things like the edges, right? I already told you what an edge is. Basically, if you're painting a picture, what would you draw as a line or a stroke? That's what we call edges. You identify those edges, you identify simple lines, right? The middle layers of your network, that is the deeper layers after the first initial layers, maybe layer 1 to layer 3, or layer 4, layer 5, or layer 10. The middle layers from layer 11 to 20 will begin to start identifying combinations of the first layer. So remember, more complex is basically by combining. So if I'm able to identify edges, the top edge, the bottom edge, or a vertical edge, a horizontal edge, the middle layer will combine a vertical edge and a horizontal edge and identify a corner. Because a corner is basically a combination of a vertical edge and a horizontal edge, right? And by the time you combine different edges like that, you can also get textures like a hash texture, right? That can be a combination of 3 or 4 vertical lines or 3 or 4 diagonal lines that will give you a hash texture. Okay. And then the deeper layers begin to combine these textures to form shapes, right? And then the shapes will also combine to form objects. So rather not forming, but to identify, it learns to identify shapes by combining the features in earlier, the more complex features like textures and so on. Corners and textures can be recognized. Those features can then be combined to form a shape. A shape is basically when you identify multiple corners that are enclosed, and then textures that mean maybe the color or the roughness or smoothness of a surface, okay? And then the objects will be shapes that you are able to identify multiple shapes. So then, of course, I talked about translation invariance as well, which means that because we are using kernels that can move across the picture from left to right, up to down, scanning it, right? It's able to identify these features no matter where it is on the image. As long as it's the same feature that that particular kernel had learned how to recognize, it will recognize it. Okay? And the reason for this, like I say, is this reduce sensitivity to exact position. So that's why the convolutional neural networks will work very well for object detection, for face recognition, and medical imaging, as well as others. So these are some of the additional concepts we'll talk about convolution filters. I've been mentioning this, feature map stride, padding activation function. Well, we've talked about activation function already. ReLU is used mostly for image for CNNs because it's very fast and it also is able to pass across positive features while it truncates the negative ones. Then we have pooling, we have max pooling and average pooling. We'll talk about that. The stacking of the convolutional layers, which results into this spatial hierarchy of features that we talked about. Receptive fields, which are you know, we've mentioned that already. The fact that these models will only see parts of the image, right? So it has a narrow receptive field. It's able to see that and identify weight sharing. We've already talked about spatial hierarchy, flattening, and all of that. So we'll take some of this one by one. So again, let's look at this, and I'll try to explain, with this image. So the concept of a kernel, okay? This each of these things here can be considered as a kernel. And I'll break down kernels even further, right? The jumping into three-dimensional makes it a bit more difficult to understand. But we'll start with two-dimensional and we'll talk about convolution and then we'll do a bit of animation. But each of these is what we call a kernel or a filter, right? And what it does is it identifies features, okay? When it identifies, so each of these 9 kernels, there are 9 kernels here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that also arranged in a two-dimensional grid. Now, each of these kernel is going to scan through an image from top left to bottom right, okay? By scanning it, leftwards. It starts from the top left, it scans to the end, it moves to the next line, it scans, it moves to the next line, it scans, it moves to the next line, it scans. That's how it works. And then when it does that, by the time it finishes scanning each line, it gets to the bottom line, which is at the bottom of the image, right? And then it scans all the way to the bottom right. Each time it scans, it is going to generate a single feature like this. And that feature it is going to generate, that's what we call the convolutional result. That feature is going to be it's going to result from a convolutional operation, an operation called a convolution. So that convolution, what it does is it combines the features in that particular area that it has scanned. For each step, it combines that and it comes up with a single value that represents all of what it has identified, essentially the feature it has identified or it was trained to identify in that subset, right? And then this will be the feature it will transfer to the next layer. Okay. So to go with what I had said earlier, this this is the kernel. The kernel is going to do a convolution and it's going to come up with this, right? And this will be transferred to the next layer. So you will now see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 kernels. So each of these kernel is going to generate its own. So this one will generate a single output that corresponds to the feature it has been able to detect, and it will send it to the next layer. This kernel will also generate a single output and it will drop it here. This kernel will generate, so each of these 9 kernels will generate each of these outputs. So that's why you now have that this output is also a 3 by 3 matrix that is made up of the outputs generated by these 9 kernels. Okay. And that's why you see that this 1, 2, 3, 4, 5, 6, they were looking at large sections of the image, but they come up with a single value. So in this way, they have been able to extract a feature, what they have, each of them has identified. And I'm going to go into a bit more detail. Again, it is important to understand this intuitively before we go. At least understanding it helps for you to understand how the CNNs work. Okay. And then this image is to kind of illustrate that when we say that the CNN uses this spatial hierarchy, right? This is the hierarchy. So this is a hierarchy, okay? Each layer, so you have this first layer, okay? You have one layer, conv2D layer, and this conv2D layer, right, is made up of a matrix of kernels. So this layer may have 9 kernels, like we saw. 1, 2, 3, 4, 5, 6, 7, 8, 9. So effectively, this single layer, okay, has, let me show you. So let me connect the dots. This single layer has, you can think of this single layer as this, right? Okay. So you can think of it that this, you can think of it that these 9 kernels, okay, form a single layer. These 9 kernels form a single layer, and they will generate an output that is made up of 9, a grid of 9 by 9 images, okay, or 9 by 9, not really images, 9 by 9, a grid, 3 by 3 grid of 9 features. The 9 features it has identified in that image, okay, assuming they just scanned it once. So again, there's more to that we're going to look at. This is not, I'm going to progress to get us to really understand this. But let's think of this as like, okay, this is a single layer, okay? Even though it's not necessarily so, but let's think of that as a single layer. So that single layer is this, right? So this single layer is going to also generate features. This next layer is going to generate features to this next layer, okay? And on like that. So in this particular network, you see that you have a conv1, layer, and then you have another layer here, right? But this layer has a stack of additional things in it. And then you have another layer here, right? And then you have another layer here, right? But each of these has filters, and so on. We are going to look at all of this in detail. But this is just the idea when we say spatial hierarchy of features or of feature extraction. It means that this first layer will extract some features. This next layer will take the features that this has extracted and extract some more complex features and pass it on to the next layer, which will also take the more complex features this one previous layer has extracted and extract even more complex features. Okay. All right. So now let me explain this what we mean by convolution. So remember I have said that a single filter or kernel, right, uses the principle of convolution. So convolution is a fundamental mathematical operation that extracts the spatial features like edges, textures, and shapes from data. So this data, remember, it comes as a grid of pixels. And remember, pixels are basically numbers. It's four numbers that represent the red, the amount of red, the amount of green, the amount of blue, and the amount of alpha, which is the transparency. Okay. So I'm going to go look at some animation so that we can understand. Now, when so a kernel is designed essentially to extract a feature, but the mathematical operation that it does is this. Let us assume that this particular um, grid at the back contains the image information. Okay. You can look at this. So let's take a black and white image just for simplicity. Remember I said that RGB, color images have, for you to depict color, you have to use the red component, the green component, and the blue component. So you need 3 data points for a color. But let's simplify just for the sake of this explanation and say we are dealing with black and white colors. So for black and white, you don't actually need RGB. You only need a single value, a single number to represent black and white. And it is either 0 or 1. 0 means black, there's no color there. 1 means white, there's color. Or let's extend that to what we call grayscale. Grayscale is black and white, but it's not all black and white. You have shades of gray in it. So you can think of pictures that have shades of gray, but there is no color. So 0 would mean black, so there's no color. 1 again will still mean white. That's full white. Then 0.5 will be an ash gray color that is in between white and black, and then you have different degrees of, gradation. So I can even kind of show you that by showing you how a grayscale color looks like in case you don't know what grayscale means. Okay. A grayscale image rather. So I can go take a grayscale image. Let me show you an example of a grayscale image. Um, and I'm going to take this grayscale image, okay, and I'm going to just put it, let me just step out from and let me just put it in this whiteboard. So this is a grayscale image, okay. If you look at this grayscale image, you see that there's no color here. Everything is either white or black or shades of gray. So if we are using a grayscale image just to represent, let me add it to the slide, just to represent what we are trying to demo here. So you have a grayscale image, okay? So if you look at this image of this tiger is grayscale, and I just want to use grayscale here. So for grayscale, let's assume, okay, that this grid here, we are using it to represent the image of this tiger. Now, what will happen is that any pixel that is black, we represent it with 0 to mean that there is no color. And any pixel that is, in this case, we have numbers that are greater than 1. So let's say 0 to 256 or think of any, we can do normalization and so on, right? So let's say 0 to 9 or 0, yeah, let's say 0 to 9. So this entire grid, this 5 by 5 grid represents the image. Even though if you look at this picture, it has more than 5 by 5 pixels. It probably has 1024 by 728 or something, some of those numbers. Okay. But just for the sake of explanation, let's assume that it has 5 by 5. So it has 25 pixels in it, 5 horizontal, 5 vertical. Now, you see the numbers in here. These numbers represent the degree of grayness or the degree of grayscale. You can also think of it as this number representing the color. Okay. But remember, when we're doing color, we are separating it into RGB. But in this case, we are saying black and white. So again, 0 means black, no color. Maybe 9 means white. So 4 would mean gray in between. So if I were to take an image, right, and translate it to the color equivalent, okay, and plot it, which I'm going to show you that shortly, it's going to kind of um give you numbers like this, okay? So the 5 by 5 numbers represent the colors in this image. Now, for me to do a convolution, I would then take what we call a kernel. A kernel, we now choose a 3 by 3 kernel. 3 by 3 kernel. So this other one that you see here that has this number 021, 410, and 101 is a kernel. And I'm just using it as a two-dimensional kernel to extract just a single feature. It is not extracting more than that, right? It's just extracting a single feature from this image. So this kernel is going to do what we call a convolution operation. And what is happening basically is you are overlaying a subset of this image that is the same size as the kernel, and then you are doing a mathematical operation. In this case, a mathematical operation is a simple element-wise product. You are multiplying 9 times 0. Then you do a sum of the element-wise products. That's what this particular kernel is doing. And in most cases, that's what most kernels do, is a sum of element-wise products. So you take 9, you multiply by 0, you store the results, okay? You take 4, you multiply by 2, you store the result. You take 1, you multiply by 1, you store the result. So what do we have? We have 9 times 2, 9 times 0. So just for clarity, in case you did not understand when I was saying 9 times 0, 9 times 0, okay? 4 times 2 and 1 times 1. Because essentially I'm taking this kernel here, right? And I'm overlaying it on top of this image, this subset of this image. And think of it like a filter. Well, that's why it's also called a filter, but a filter is slightly different from a kernel. I'm going to explain the difference shortly. But let's start with a kernel. A kernel is a flat two-dimensional structure that you overlay on a part of a section of the image. And that section of the image that you overlay it on is going to be the same size as the kernel. So you then do the maths, right? And the maths here is simple. Sum of element-wise products. So you have 9 times 0, okay, plus 4 times 2, right? Plus 1 times 1, okay? You still continue, plus you now do the next row. So remember the first one, we are doing this we are doing this first row against this first row. Then we'll come and do the second one and we'll keep adding. So 1 times 4 plus 1 times 1 plus 1 times 0. And then that's the second row. Then we'll continue with the third row. So in the third row is this, right, against this. So 1 times 1, okay, plus 2 times 0, right, plus 1 times 1, okay. And then we do this total sum. And that's what you are seeing here, okay. And that total sum gives you 16. That is the outcome of that convolution operation. So the convolution operation is basically sum of element wise products when you apply a filter to a subsection of the image. Okay, that gives you the convolution. And you can see the result of that convolution is placed here. Why is it placed here? Here corresponds to this top left position. Okay. We can now do another convolution on the next one, right? In other words, this 2, 2, whatever is here, 0, 4, whatever is here, and the result from that convolution, we'll write the answer here. And then we can do another convolution, assuming this image was extending all the way this way, right? And all the way down, okay? We'll do that convolution. Then we'll now move this kernel down, okay? Notice that I am skipping entire this thing. So we'll talk about what we call stride and overlap. So 0 times 1 plus 2 times 0 plus 1 times 0 plus 4 times 9 plus 1 times 6 plus 0 times 7 plus 1 times whatever is here plus 0 times whatever is here plus 2 times, I do all of that. So, and that gives me the next, um, the answer here. And I just keep doing that. I'll get different answers. These are just random numbers I am coming up with, right? But the fact of the matter is that we will end up with numbers, and this whole operation is what we call the convolution. So this is a sliding window operation. We are taking this kernel and we are sliding it across the image. And at each point, we do a calculation of the convolution. We store the answer here. We slide the kernel to the next, you know, subsection of the image. We do the convolution and we store it. And we keep sliding it all the way right to the end of the image, to the left, to the right boundary of the image. And then when we are done, we move it down and continue at the next line. So think of it like, again, a typewriter. I like to use that. So by the time we've done that, we have generated this new output. This output from this convolution is the new set of features that will be sent to the next layer, right? And that is the convolution. So convolution involves sliding a small filter. So let me clear this so that I can make my sketches much easier to understand. Convolution involves sliding a small filter. This is a small filter that we are sliding. This square here that has these 9 numbers. We are sliding this small filter and we are sliding it rightwards. Okay. That small filter is called kernel. Technically, the name is kernel. Then when it is 3-dimensional, it's called filter. Even though it's people also call the one dimension, the flat one, the kernel. So you slide it across an input, such as an image in this case. And remember, the image is represented by numbers. So you have to convert the image to numbers first. When you do that, you calculate a new feature map. So this is a new feature map that you have calculated. You calculate a new feature map, and that new feature map is this one. Okay, that's a new feature map that we calculate. This is a new feature map. And this new feature map is going to map to the number of windows that you arrived at in your sliding window. So you slide it across the input and you calculate a new feature map by multiplying the filter values with the input pixels and summing them, right? This is the most important part of it. Multiply the filter values. Okay. So once you do this, then essentially your model begins to predict. So in all of these 3 things we have talked about, which one is the model? Which one are you training? It is a filter. It is a filter that has parameters. It is the parameters of the filter that will determine what it is able to detect, right? This input image is just an input, right? That just comes into the image. The filter scans this. And then the output array is the output from the filter that will be sent to the next layer of the convolutional neural network. So you can see that this kind of gives us a very good representation of it. This is in this corner, think of it as this. It is now a three-dimensional representation of it. Okay. In this three-dimensional representation of it, you can see that this, right? Think of this as this section. It's just taking a, scanning this section first. It reads it, it does, this is the filter itself. This one is a filter, right? Or the kernel. It does the summation and it sends the output to the next layer. So this is the output that comes out from it, okay? And this is just a single section of the image. The next thing is going to scan the next section. It's going to scan the next section. It's going, just remember it's a sliding window that goes to the right and then gets to the end, comes back and does that. And that's how convolution happens. So when you hear convolution in the context of neural networks or the convolutional neural network, that is what it is, okay? So this is kind of an animation that tries to depict that. In fact, I'm going to make this animation much bigger and perhaps fill this entire page because really it is so important for us to understand, this whole convolution animation and how it works, right? So I'm going to just fill up the whole page with this and I'm going to allow us to see. So look at it very carefully. So the inner square that is shaded is the kernel. And then the outer square that is blue is the input grid that represents the image. The image has been converted to the pixel values. Now you will see that when it is here, if you look at the kernel, you see the values inside the kernel. You have 012, 220, 001. Those are the learned parameters. Those are the weights that that kernel has learned. It has learned those weights. It will now take those weights and multiply. So remember, in a fully connected neural network, you are still multiplying weights by inputs. And then that sum of the weighted product, the product of the weights is what you add. You sum it and that gives you the intermediate output in that neuron. That is then you now do what do you call it? You now apply the activation function. So it's the same principle here. You have 0, 1, 2. So if you look at this first one, I take 0. Unfortunately, there's no way for me to pause this animation. But I take 0, I multiply by 3, I get 0. I take 1, I multiply by 3, I get 3. I take 2, I multiply by 2, I get 4. So that's 3 plus 4, 7. Here will be 0, 0, still 7. Then I multiply this, is still 0, still 7. Then here is 0 again, so still 7. Here is 1, that's 8. And here is 4, 8 plus 4, 12. So that gives you the 12 that we get from this first section. Then when it slides, you can see that it's sliding, it slides by 1 pixel. It doesn't slide the entire width of the kernel. It just slides by 1 pixel. It does the same convolution operation and the result again is 12. It puts it here. It slides again by 1 pixel and you get 17. Then it moves down to the next line and again it starts from the beginning and does the same thing and goes, rightwards. It slides, you get 10. Slides to get 17, slides to get 19, slides to get 9, 6, 14. So you now have the output. The interesting thing you notice that the size of the output is smaller than the input. The input was 5 by 5, but the output is 3 by 3. The size of the output is not the same as the size of the kernel. Here is just a coincidence. The size of the output depends on the number of, times it is able to slide before it gets to the end. So you can see that here it slides 3 times before it gets to the end. 1, 2, 3, it gets to the end. That's why you have 3. Again, 1, 2, 3, it slides 3 times, it gets to the end, and then it moves to the next one, it slides 3 times, and it has finished vertical. So the output matches the number of times the kernel slides before it gets to the end. Okay. So that's convolution. Now I'm going to go do another animation. This one is going to really give us a really good idea, right, of this convolution in 3 dimensions. So remember, if you look at this, This is just a single feature that is sending out. But in CNNs, each layer does not just send out a single feature. So think about this thing that we are seeing here, okay? And we're going to talk about kernels and filters, which is what does the convolution. Now, think about that this is just a single feature, and then think about that we had each kernel generates a feature, and I had 32 kernels, okay? That means we'll have an output that has 32 features. That leads to the next slide. You can now see that we now have a three-dimensional thing. This is a single kernel. It extracts a single feature, right? But if I have two of it, I can extract two features. If I have 32 of it, I can extract 32 features. So we now stack this in the third dimension. So a filter is a three-dimensional shape where the two dimensions here represent the kernel and the third dimension represents the features. In other words, the number of kernels that are generating those features. So if a layer has 32 filters or 32 kernels, it will produce 32 feature maps. Each map answers a different question about the image. In other words, each kernel generates a feature map. Okay, so 32 kernels or 32 filters will generate 32 feature maps. Some of the things that the filter will identify will be vertical edges, horizontal edges, diagonal edges, texture blobs, and so on, right? So I don't need to say this again, right? A filter is basically a small matrix, 3 by 3, 5 by 5. What I showed you here was a 3 by 3 that is able to extract a feature. It is filled with learnable numbers. In other words, these numbers that you see inside the numbers are actually moving, not the static ones, the 0, 1, 2, 2, 2, 0, and 0, 1, 2 here. Those are the parameters, same as the weights and biases that you have in a fully connected layer. But those are the parameters, and those parameters are learnable. In other words, when you do back propagation in a convolutional neural network, these things, those parameters will change. They are learning how to identify features. It is random at start. Remember, parameters, we always initialize them to random numbers. But after you train it, it becomes meaningful. It has learned how to identify a particular feature. You may not know what that feature is that it has learned to identify. It will not tell you what the feature is, but you can use these feature maps to kind of identify what it does. We'll talk about feature maps. So a feature map is basically the output that you gain when you apply one filter. In other words, you take this filter, right? This is a single filter we apply across. So this output that you have here that has 12, 12, 17, 10, 17, 19, 9, 6, 4 is a feature map. If I were to take this and plot it and turn it into colors, remember everything starts with colors. We convert the colors to numbers, right? The colors in the pixel, convert them to numbers. Now, after we've gotten a feature map, we can visualize that feature map by taking the numbers that come out from it and again display them as colors, right? So that's what a feature map is, basically taking the output from one filter, right? And then you plot a two-dimensional grid, okay? And then you convert each number back to colors just to show how it looks. So you see how this looks. This is a feature map, right? Bright areas, remember I told you 0 means no signal, black. 1 means white, okay, full signal. So bright areas normally show that if there's a full signal from that particular feature. So it means it has identified that feature. Bright areas mean that particular feature that this particular kernel or filter has learned to detect is prevalent in that area. So for example, if you look at this, you see that you have this bright section. It means I can see an edge or a diagonal line here. Whatever this particular kernel was trained or learned to identify, it sees a lot of it in this area. This other one is from another kernel, right? This other one is from another kernel. And you can see, again, it is now identifying features in a different manner. So bright areas mean I strongly see I, as the kernel, I strongly see the pattern I was learning to identify in that area. Dark areas mean I don't see it. In fact, it's almost not uh, available there. Now, if you look at this entire thing, you see that there's a pattern. The different kernels identify different kinds of edges. So you see edges here, an edge that goes this way, and an edge. This one is even two edges, an edge, two edges, that are kind of horizontal. This one is diagonal in this other direction. This one is a boundary. You can see one side here, one side here, and so on. This is another boundary. You see one side up and one side down. And then you see here, again, edges. So you see that's what it identifies. This is the first layer. So you now see the layer-wise meaning. You see that this is layer one, it's identifying edges. Layer two now is able to combine the features it has identified, the previous layer has identified, it is able to identify more complex features. So here now is identifying circular kind of features. Here is identifying curves, right? Here is identifying repeated lines. Here a single straight line and so on. Here you can even see a curve and so on, right? Here you now have not just boundaries, but shapes, enclosed, shapes. So you have an enclosed shape where the inside is identifying it with this green color, while the border is this magenta type of color, and so on. So you see all of this. This is second layer of the network. The third layer, you can see it is a bit more fine-tuned, giving you more interesting shapes that it has identified. You can see this one is concentric circles. This one, another concentric circle in different. Some of this could be eyeballs, people's eyes, or anything that looks like circular. It begins to identify. So this is what we call the hierarchy, right, of features that we get. So you now begin to see the early feature maps. Early, what I mean by early is early in the layers. The earlier layers will begin to identify simple features like edges and simple shapes that you can see here. Then the deeper features, you start seeing parts of objects, right? And then detail objects. So these are the feature maps, okay? Then we now apply what we call pooling and spatial reduction. So pooling is a way to downsample the different features, and you typically place immediately after convolutional layers so that it can reduce spatial dimensions of feature maps while retaining essential information. The issue is that feature maps can become very big, right? So you can pull to get smaller feature maps. So for example, you have a feature map that is 128 by 128. You can reduce it to 32 by 32 by using pooling. So it's a critical technique for reducing computational load, because as the feature maps get bigger and bigger, remember the larger the number of pixels, the more the computation you have to do. So sometimes we can reduce the computational load, right? So that your model can train faster, or to prevent overfitting because the features are too many. The generated features of the subsequent layers are too many, right? And then to build robust translation invariant representation. Remember, I talked about translation invariant. It doesn't matter where the cat is, you still recognize it as a cat. Okay. So pooling layers help to do that. Okay. So pooling operates on small regions of a feature map, right? It's example 2 by 2 windows, and summarizes them into a single value, right? It helps with dimensionality reduction by shrinking the spatial dimensions. Like I said, for example, halving the width and the height, and pooling significantly decrease number of parameters and computations, and translation invariance. So basically it's the same thing we have said. The common types of pooling that we have max pooling. So in max pooling, you can look at a small section, the same as the section, and we're going to look at more of that next week when we come, because we run out of time. But we'll take time and look at that. So you can look at this section. Let's assume that this is the output, from a convolutional layer. You want to reduce, you now have a feature map that is, in this case, 3 by 3, but let's say you have a feature map that is large, maybe 128 by 128. You can now do max pooling. Max pooling is basically the same way you would do the convolution itself. You apply a kernel across, and in that kernel, instead of doing product of weight, By the way, pooling layer doesn't have parameters or weights. What it just does is if it looks at the number, the total, looks at the output, right? In that area it's looking at max pooling, it will take the maximum number. So in this case, if I were to apply max pooling here, the output from this will be a single output of 2 because 2 is the maximum in this. Here, I'll look at this, it will also be 2. But average pooling will calculate the average of these outputs. So that's the main difference. We'll look at it more. Then global pooling reduces an entire feature map into a single value. That is, it looks at the entire feature map. And you normally use this at the end of the network when the network has finished, at the last layer. That's what it means at the end of the network. When all the layers at the last layer, use it to extract the classification because typically you want to use it for classification. So we're going to come back to look at this because I've run out of time. I want to just do a little bit of the animation of how all of this works so that we can understand a bit better. There are other animations of how convolution works, the convolutional neural network works. So I'm going to just give me a second. And I think we can just end with those animations. Okay, so let's take a look at this, right? I'm going to play this video, okay, just to help you, and I'm going to make some commentary. I'm not going to use a commentary in the video itself, but I'm going to make my own commentary just to help. So, yeah, this is courtesy of animated AI. So the first thing is this, right? This is typically how, I think I've already showed this. Okay, you have a situation. Think of this one down here as the input image, right? Down here is the input image that you want to do convolution on. Okay, and this is the image. This is the output. Okay, then they use a shadowed section to represent the kernel. So as the kernel is basically sliding right to left, sorry, left to right across, it is generating this. Okay, and that's kind of um this is just a single feature, right? A single kernel is generating a single feature. So that's typically how, yeah. So now, um, I'm going to move to, you see a lot of animations, right? So again, same thing, right? Now, let's go to, this is kind of a graphic of a full stack of a model that does image classification or recognition. So you see what's going on here. There's a lot going on here. They even have a convolution network and a deconvolution network. Well, this is kind of a encoder decoder. It's not a classification model. I guess it's encoder decoder. So here you have the image. You can see the image here of a dog. Then that image of a dog is a 224 by 224 image of a dog, right? And you can see it has 2 layers. So these 2 layers, first of all, correspond to the original features of the dog, which are just the pixels. Okay. Then you now have a kernel that will then take this one and it will scan through it and it will give you an output that is a 112 by 112. Then this 112 by 112 will be passed through a max pooling. Sorry, an output that is 224 by 224. Okay. Then this 224 by 224 will pass through a max pooling that will bring it down to 112 by 112. And then you do another convolution on it. And after you do 2 layers of convolution, and after that you do a max pooling that will bring it down to 56 by 56. Remember, max pooling always reduces the dimension. And we'll explain how that happens by next week when I come next week. When we meet next week, we'll talk about max pooling in detail. And then, it just keeps going that you keep seeing that anytime you have a max pooling layer, the dimension of the output reduces by half, basically, from 224 to 224 to 112 to 55 to 56 by 56 to 28 by 28 to 14 by 14 to 7 by 7. And then the last max pooling layer will take it to 1 by 1. Basically, 7 by 7 is flattened out. And so we'll talk about this when we look at specifics of the architecture of the convolutional neural networks. You see that most of them are kind of the same, right? If you look at this, right, this is one direction. Again, you see the pixels are, first of all, this is 96 by 96, so you have 96 by 96. Then you will have convolution and then max pooling that brings it down to 256. Okay, sorry, this is 96 by 256. And then you have 384 and so on, right? So, but let me get to the, let's go look at a 3D animation. I want to arrive at a 3D animation of how the, yeah, so let's look at this. So if you look at this, before I run the animation, right, this is like the best animation. This video is actually about different animations for convolutional neural networks, and they're all not very complete. They don't give you a very good idea of what's going on. This, to be honest, is the one, and I agree with it fully. Now let's explain this animation. Let me kind of explain it. So the first thing that you notice here is that there are 3 sets of cubes. Okay. This first cube here represents the image, right, that we are trying to learn how to detect. So this is the image, okay? The image, right? That's this first block here. Let me use text. Yeah, so this is the image. Now, you may ask yourself, but images are 2-dimensional. So why is this one a cube? So let's think of the third dimension as the RGB, right? But it is a more generalized thing because it also represents the input from other layers, other convolutional layers where features have been extracted. So it's always going to be, let's say W by H by, let me just use D for depth. So W is the width, H is the height, So you could say that this is the W, okay? This is the W, right? This is the H, and this is the depth, okay? So this is the image. Now this is the kernel or the kernels. I would call them kernels or filters, right? Let's call them filters or kernels, right? Now these are kernels that are 3 by 3 by, yeah, so let me even do that. So this is 3 by 3 by 1, 2, 3, sorry, by 8, okay? So this is a 3 by 3 by 8 kernel, okay? And there are a number of them. So again, let's go back again. So let's go back again. Right. So this is a 3 by 3 by 3 these kernels, 3 by 3 by 8. So you can see it has 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 3 by 3. And then it has a depth of 8. 1, 2, 3, 4, 5, 6, 7, 8. Now again, this is a generalized case where the depth of the kernel needs to match the depth of the input that it is kind of analyzing, if I might put it that way. Okay. So the reason why the original filter that I was talking about was depth of 1 was because I was using RGB image also has a depth of 1. Sorry, not RGB image, a grayscale image, a black and white or grayscale image that only has 1 input feature. right? And that input feature is just the color, which is a number from 0 to whatever. Okay, 0 to 9. So um so the depth in this case is 1 for an image. Okay. So let's say depth equals to 1, right? In the case I was doing, but here depth equals to 8. So you can see here the depth is 8. 1, 2, 3, 4, 5, 6. So there are 8 different stacks here. The depth here has to match the depth of the kernels, right? Because each part of the kernel, each um, two-dimensional piece of this kernel or filter will only analyze one of these, okay? Then you have n filters here, right? So the number of filters is n, okay? Right? The number of filters is n. And this is very important to understand that right now we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 filters as well. So what will happen is in a real convolution, each of these filters, okay, will come in and they will scan this thing left to right, like we said, okay. It will scan it left to right. And yeah, so it will scan from left to right. I'm trying to get this to start at the right spot. So it will scan and extract the features, okay. So you can see it's scanning. When that kernel is done, another kernel comes in and scans in. And when this scans and does a calculation, each kernel gives out exactly one solution, one answer. That answer is the sum of the what do you call it? Sum of the element-wise products. Okay. And that's basically what's going on. So each of them, there's a website. I'm going to share a link to the website where you can see various animations of this, So this is kind of for me the best animation that really shows how these things, so it gives you a mental image, right? Of how this works. And this is the website, right? You can see there's a bunch of animations. So for example, this is animation of scanning, right? You can see um, each kernel comes in, it scans that whole thing from left to right. And as it's scanning, each of the two-dimensional pieces of this filter handles a two-dimensional piece of the input, right? And then their output, they send a single output, that forms another tube, three-dimensional output. So you can see that this three-dimensional output is made up of a stack of the features extracted by each kernel for each section of the image, okay? For each section of the image. So it basically takes that, and that is what is going to be sent to the next layer. And you can see that this basically resembles this. So the next layer will also need filters that look like this to scan through all of this and give us that. So, and there's a bunch of other animations that demonstrate other things as well. Um, so I encourage you to go check this out. We're going to talk more about some of the things that matter with convolutional neural networks. So when we talk about things like this, the stride, right? The stride length, the padding, right? We've already talked about filters and so on. So I'm going to pause at this point. I know this was a lot of theory, right? But I was trying my best to give you the intuitive idea or knowledge of what convolutional neural networks are. Now you may still be asking yourself, okay, so how does this translate to me being able to do image recognition? We will go into that when we come. So I hope you enjoy this class, and thank you.